Welcome back, Bio10 students. You may be happy to know that this is the final screencast playlist for the atomic theory of matter, but you may be unhappy to know that your lessons in chemistry don't end with this. This is really just the beginning. After your first midterm, we're going to get back into chemistry in a lot of detail, but we're going to talk about the chemistry of cells and living things, specifically about their metabolism. So since metabolism is such an important characteristic of life, the chemistry that is metabolism is going to come back at you again and again and again. So don't think that just because we pass this chemistry unit that chemistry is gone from the course. This was actually all just to give you background so that you can really understand the metabolic chemistry of living things. We did start to talk about chemistry last lecture when we talked about how metabolism involves chemical reactions, changing one set of chemicals into another by breaking bonds and making new bonds between atoms. And we talked some about the metabolism of your body and how that relates to diets and to some extent to exercise and how those things can influence your metabolism and how your metabolism explains how you process food. So today in this last atomic theory lecture playlist, we're going to talk about a different property of chemicals, not the reactions that they do, but the movement that they make. How do chemicals move? So the topic today is molecular motion and how that's related to some properties of motion called diffusion and osmosis. Both diffusion and osmosis are properties of chemicals that require molecular motion and that involve the motion of molecules. But to understand these important concepts, you need to understand the basic theory of motion, of how molecules move. This is different than the theory of reactions. Molecules can move without actually changing. This is just talking about how they move through space, even when they're not reacting with each other. So the first thing you need to know, there's just a few simple rules of motion, but they lead to some very powerful ideas and ideas that explain a lot about the world that we see around us and about what's going on in our bodies. So the few simple rules of motion, first of all, molecules are always moving. So if it's a molecule, and it doesn't matter what kind of molecule, if it's water, if it's sugar, if it's fat, if it's protein, if it's salt, if it's gas, if it's a molecule, it is moving all the time. So the word constant means it never stops. Random means the motion doesn't have a particular direction to it. Chemicals basically move in a straight line until they bump into other chemicals. And then they either react with them or they bounce off and move in a different direction. So today, since we're just talking about motion, we're not going to be talking about the reactions that happen. We're going to be talking just about the movement. So we're going to assume today that when molecules run into each other, they're just bouncing off and going in a new direction, but they're not actually reacting. Now, there is a direct relationship between the temperature and the speed of molecular motion. And it's very basic. The higher the temperature, the hotter it is, the faster molecules are moving. So when it's cooler, molecules move more slowly. When it's hotter, they move faster. But they're still always moving. So even if you make the temperature very cold, like freezing temperatures, and even below freezing temperatures, molecules are still moving at those temperatures. They're just moving a lot more slowly. Now, as you heat things up, molecules move faster. And this is a little bit of a relationship between chemical reactions and motion. Reactions occur when molecules run into each other but don't just bounce off. When they actually run into each other and hit each other with enough force that some of their bonds break, and then they can exchange atoms. Now that usually only happens at higher temperatures because the hotter it is, the faster molecules are moving. And when things hit each other moving faster, there's more force involved than when they hit each other moving slower. You can think of this like you would think of a car accident. If two cars hit each other going only 5 miles an hour, there probably won't be a whole lot of damage to the cars, not a lot of braking. But if two cars hit each other going 50 miles an hour, there's going to be a lot of damage and a lot of things are going to break because there's a lot more force in a 50-mile-an-hour collision than in a 5-mile-an-hour collision. So that means that the hotter it is, the faster molecules are moving. The faster they move, the harder they hit each other. And the harder they hit each other, the more chance there is that their bonds will break and they'll do chemical reactions. So this is why, if you've ever had a chemistry class, you'll note that a lot of the reactions you have to do in that class, you do at higher temperatures. You tend to heat up solutions or boil them in order to make the reactions happen faster, because that extra heat provides more motion, faster motion to the molecules, and then they hit with more force and they're more likely to react. This, by the way, is also why your body temperature has to stay around 100 degrees Fahrenheit, because at that temperature it's warm enough for the important chemical reactions in your body to actually happen. If you cool your body down too much, the chemistry of your body, your metabolism, slows down dramatically because the reactions slow down dramatically. And if you cool down too much, your reactions can't happen fast enough to actually keep you alive. For example, when you cool down a human being, their heart beats more slowly. The contraction of the heart muscle involves a lot of chemistry and chemical reactions, and those reactions happen slower at lower temperatures. So once you get down to body temperatures below, say, 90 degrees, the heart is hardly beating at all. And obviously that is not too good for our health. So I wanted to illustrate the motion of chemicals, what random motion looks like. Turns out that there's a lot of nice molecular simulators on YouTube. So this video is a molecular simulation where each of these little dots represents a molecule. And we're going to put all these molecules into random motion. So they're just going to, each one's going to move in a direction and continue in that direction until it hits another molecule and bounces off. And so you can see here's what random motion looks like. And what this simulator is doing is it's actually tracking the motion of this one molecule. And you can see that one molecule is just moving straight until it hits another molecule, and then it bounces in a different direction until it hits another one. And so you can see the path of that one molecule is pretty random. It goes this way and that way, and there's no real clear direction to it. Now, if I back this up, you can see the effects of temperature on molecular motion. So I'm going to slow down the playback here. And so this would be the motion of these molecules at a much lower temperature. And you can see it's the same motion, but it goes a lot slower at a lower temperature. And then if we heat things up and make things even hotter than they were initially, you can see the molecules move a lot faster. So that's the difference in molecular motion between slow and fast. It's not a difference really in how they move, just in how fast they move at the different temperatures. Okay, so hopefully that illustration was clear, and in the next video we're going to go on to what happens as a result of the fact that the molecules that we're made of are always in motion. That creates an interesting phenomenon called diffusion, which is really, really important to understanding how living things work.